Welcome to Ask and Learn.
And in this case, we have a bar that's swinging at a pivot here, and it has there's a couple of springs attached at the mid length. So the total length is 4 meters, and the springs are attached 2 meters down. So we have our potential energy is elastic energy in the springs and our gravitational energy. Now, if we measure the gravitational energy from, let's see here, from this point here, we get minus mg, and then y, the distance, the vertical component of the center of mass, is L over 2 cosine theta. And then we have 2 times the spring elastic energy, which is 1/2 k times the change in length squared. And again, the change in length of each spring is going to be the same, at least for small motions. Now, the change in length we can approximate as L over 2 theta. Okay, so that's the approximation of the horizontal displacement of the center of this bar is approximately this, if theta is small. And likewise, we can approximate cosine with 1 minus 1/2 theta squared. And so, in fact, I should actually put a minus mgl over 2 in here, but that actually winds up dropping out, and we don't really need to worry about that. Because when we take a time derivative of this is a constant, so that goes away. So when we try to find the equation of motion, this constant term is not doesn't contribute. So then we get 1/2 mgl over 2 theta squared as an approximation for this. Now for kinetic energy, we just can take the kinetic energy of the bar rotating about one end. So J in that case is 1/3 ml squared, and the angular velocity is theta dot. So we can see here now that we have an equivalent mass right here, and then the terms from our equivalent stiffness, we have, let's see here, we have k L squared over 4, but we need to pull 1/2 out of here, so we have k L squared over 2, and then we have the rest of this here, mgl over 2. So, the kinetic energy term would look like this, right? And so this is if we pull the 1/2 out of everything and the theta squared out of everything, we would get this in front of our theta squared, our quadratic term, right? So our natural frequency is the square root of this divided by this. We can, an L will cancel out, and we get 3 times KL plus mg all over 2 ml, and we're given values for all of those things, and omega n is then 7.33 radians per second, and in terms of hertz, it's you just need to divide by 2 pi, and that's 1.17 hertz. So in this problem, we were asked for the natural frequency, so we weren't asked for the period. The period would be 1 over this value here.